Okay, let's go to chapter 2.
Good afternoon, everyone. So we'll be discussing
You're
chapter 2.
too soft spoken. Move closer to the speaker.
Good afternoon, everyone. Sappada. Okay, so we'll be discussing chapter 2 today, working with text data from the Build a Large Language Model from Scratch by Sebastian Rashka. So just quick note from last week. So Amrali gave the chapter 1, and here's the video recording of that. So in this, so in this chapter, we are mainly looking at this stage here, which is the data preparation and sampling. And the aim of this chapter is, first of all, to prepare input text for training LLMs. Second one is to understand advanced tokenization schemes. And the third one is to implement a sampling and data loading strategy. So as you can see, the pipeline has like different stages. So in this one, we're focusing on how to create the input text. So more specifically, so if we have an input text, for example, here, this is an example, we'll learn how to tokenize the text and then create token IDs and then create the embeddings. And then, so by understanding this chapter, we understand that what it takes to process simple raw text and make it into a format that is understandable for the neural network, which is the next stage, which is the GPT-like decoder-only transformer. So, so the end goal is to understand the token embeddings. So what is word embeddings? So that's the main thing we want to understand. I asked different LLMs about this. So how would you sum up embeddings for LLMs in a single phrase? So what ChatGPT says, it's transforming textual data into numerical representations for enhanced understanding and processing by large language models. And then when we look at Copilot, Copilot says its embeddings are high-dimensional vectors that encode semantic contexts and relationships of data tokens, enabling nuanced comprehension by LLMs. And the third one is Cloud, mapping words to numerical vectors. Very simple.
I like Cloud.
Me
I think
too.
Cloud wins here.
So, and what does the book say? So the Sebastian in the book, in the chapter, says it's basically a mapping from discrete objects such as words, images, or even entire documents into a continuous vector space. So what is this continuous vector space? It's a format that the neural networks can process. So if we look at it, it can be used for different formats, like as I mentioned before, like videos or images, audio, text samples, each having their own embedding model, and it will create the embedding vector. So in this case, in this example, it's a three-dimensional vector. So as you can see, if we think of it as coordinates, so these would be different coordinates in the X, Y, Z space. So if we take a two-dimensional, just take the first two, and then we can plot it onto a two-dimensional Cartesian map there, plane. And so this is what this sample would fit in, like be mapped onto this space. This audio embedding vector would be plotted here, and the text embedding vector would be here. But this is a simplified visualization, and we can only like visualize 3 dimensions, but the vectors can go into very, very high dimensions. And the earlier algorithms that transform words into these vectors is known as the word2vec, introduced by the team from Google, Thomas Mikolov, back in 2013. The concept is the way it works is that words with similar concepts tend to have similar meaning. So by training this neural network, they were able to kind of map together different words that have similar meanings based on the concepts. So this is like the representation in two-dimensional space. So the first dimension is on the x-axis, second dimension is on the y-axis, and we can see different concepts here. And for example, here we have different types of birds that kind of cluster together. And then there's like a squirrel, which is another animal. It's not clustered within the birds, but it's still further away from, for example, countries or cities here. But so the similar concepts are being clustered closer together. So then we have the development of LLMs, which use even higher dimensionality embeddings. So for example, GPT-2 was mentioned in the book that had different parameters here. So 117 million and also 125 million parameters. The embedding space for this model was 768, and for ChatGPT with 175 billion parameters, it had 12,288 dimensions for the embedding space. So this is what we'll be trying to understand. So for example, taking what Claude said about word embeddings, mapping words to numerical vectors. So we'll be splitting the words into tokens. So tokens can be words and also punctuations. So mapping words to numerical vectors translates to mapping words to numerical vectors here in the tokenized. And then we'll understand how to create the token IDs. So here mapping translates to the token ID 8, in this example, 39 and so on. And then from the token IDs, then it will be transformed into token embeddings. So because this chapter is mainly going through Jupyter Notebook, so we'll be going through the Jupyter Notebook provided by the author. There's two main sections. So first one, it covers the section where we understand how simple text is then tokenized. And then the second section is taking the tokenized text turning it into embeddings. So let me go to the notebook. Okay, so for anyone who would like to try it out, it's in the GitHub repository. And then you basically go to chapter 2, and then the code is there. Okay, so how it's performed, just go through it. In the first part, they download a sample text, so they download the short story from online repository called The Verdict, with the total characters of 20,400. And here it's just showing an example of the first 100 characters. Wait, 99. And then the example here is what is how to tokenize the word. So it's basically doing the splits. So here, from an example here, hello world, this is a test. It's splitting by this space. But as we can see, we also want to separate the punctuations. So in the next column, they also separated the punctuations, as you can see. This is by using the Python regex library. And then empty strings are removed. So for example, here, and also white spaces. So in some LLMs, they do want to keep the white spaces, because it shows the relationship between, for example, when white spaces are imported. For example, in programming like Python, where it is sensitive for the white spaces that you need to have these indentations or white spaces, then these LLMs would encode the white spaces. But in this chapter, they for simplicity, they removed it. So they performed this strip method in the list comprehension. And what we are left with is hello, comma, world, period, this, comma, there is a test, period. And then they provide another example with different punctuations. So they want to make it more general, that it can be applied to the example text, which would be used for training. So here, similar to above, the example is hello world. Is this hyphen attest question mark, and it's broken down into the tokens. So each word is a token, and each punctuation is also a token. And here they combine the two hyphens together as a single token. So this is the example previously they provided in the raw text, which was the first 99 characters. And then they show the output. So the next step after creating the tokens, the next step is assigning the tokens, assigning unique IDs to the tokens. So basically what this is it's a key value pair table where each word is the key and the value of that key is the ID, which is in this image, it's showing brown as 0, dog as 1, and so on. So what they did is after they tokenized it, so in the pre-process is the tokenized word, we only want to get the unique values, so that's why they use the set, and they sorted it based on the default Python sorting algorithm. So it's in, and then the size, getting the size. And here's where it creates this table where it iterates in all the words and then creates the token. So the token is each word, and that's the key, and then the value pair, the value is the integer. So the integer starts from 0 because it's using the enumerate. That's the a standard Python function that iterates over a list and assigns a number from 0 up to the length of the list. And here's the example of the first 50 key value pairs. The jargon that they used is vocabulary. So this is the vocabulary. It's sorted from based on the sorting algorithm. So here, for example, exclamation mark is ID. The ID for this is 0, and so on. So and then it goes in alphabetically. So A, B, and so on. So from based on this, then we can assign each word to a token, to an ID number. So at this stage, what they did is they created a class that can easily repeat the steps above, which makes it easier. And they call it Simple Tokenizer, the version 1. They have the encode and also the decode methods in this class. So the encode converts the raw text into tokens and then assigns the IDs for the tokens. And in the decode part, it's the reverse, in the inverse. So from the IDs, then it returns back the text. Here's the diagram for that. So the sample text, the brown dog playfully chased the swift fox, is then tokenized from the encoder and provides the ID 601. And the decoding part is taking the IDs 601 and then inverse vocabulary here, which then translates 6 into the, 0 to brown, 1 to dog, and so on. And we get the original text back. So once we have this class then is instantiated using the vocabulary, the table that was created. And it is the tokenizer now as the object. And then here is a sample text also from the downloaded text, the verdict, and it is passed through the encoder of the tokenizer class. And here's the output, which is the IDs of the tokens. And this part is showing that we are able to do the inverse, taking the IDs and then decoding it back into the original text. So I guess at this point, are there any questions?
Questions? Comments?
Okay, so we can continue. The next part is, the question for the next part is, what if there are unknown words that we don't have in the original vocabulary? Or if we have multiple sources of text and they don't correlate with each other, they're separate. So how do we differentiate between these two or more texts? So this is where we add special context tokens. So after we create our vocabulary, so our first main key value pair tables of tokens and also the IDs, we extend it by adding special tokens. So for example, in this image here, it's the less than symbol and then the pipe, and between these is the UNK for unknown, and that is assigned the ID of 783. And then another special context token here is end of text, which is assigned 784. So if we look at this token ID, we can see that this token is actually unknown. That means that if we look at the original text here, playfully was not in the original vocabulary in the tokenizer. So those are just two examples of the special context, but in large language models, there are other LLMs like BOS, EOS, PAD, so padding. BOS is for beginning of sequence. So if it's at the start, EOS is another way of saying end of text. And then padding. So for example, if the length of the text is different, so sorry, the length of the text are different, what we want to try and do is create the same length. So by adding pad at the end would then generate the same length. Other ways of doing it is also just appending unknown to the end, or also end of text to the end. So in this example, we have different text that don't correlate with each other. So here we have a story, and then here is another story. Here we have some news from the financial market or something, and then another story. So how do we separate it is adding the end of text here, so that we can tokenize it much easier. So the next cell is testing this out. So using the original vocabulary that was created, they tested a new text. Hello, do you like tea? Is this -- a test? So this hello was not originally in the vocabulary. That's why it's throwing an error, so it doesn't work. And why? It's because hello was not one of the keys in the dictionary, in the vocabulary. So this is mainly showing how to add the special context tokens at the end. So after doing the creating the vocabulary in Python, you can extend it, use the extend method to add the different special context tokens. And similar to before, the vocabulary is then updated with the new IDs, and the vocabulary has now increased by 2. So it previously was 1,159. Now it's 101,061. And as we can see, when we look at the last 5 items in the vocabulary, we can see that end of text is added, and also unknown is also added. So the next step in the pipeline is they modified the simple tokenizer into a version 2 with the updated special tokens. So especially in this line here, if a token is not found in the vocabulary, then assign this token, which is the unknown token. That's basically what the update is in this encode method, and that's it. So here is an example where the first text is hello, do you like tea? And the second text is in the sunlit terraces of the palace. And they combine the 2 different texts, text 1 and text 2, with the end of text context. So this is what it looks like combined. Hello, do you like tea? End of text, in the sunlit terraces of the palace. And then we run that through the encoder of the tokenizer. And we can see here that end of text is then tokenized as ID 1159. And it looks like palace is not in the original vocabulary. That's why it's encoded as 1160, which is the last item in the vocabulary, which is the unknown. So when we decode it, it's unknown. Okay, yeah, so hello is also another one. Yeah. When we decode it, it's unknown. Do you like tea? End of text, in the sunlit terraces of the unknown. So this allows us to extend this tokenizer class for other texts that were not originally trained in the vocabulary. Okay. So there is a more advanced tokenizer that is actually being used in the models, like for example, GPT-2, which is called the byte pair encoding. So what this does is it is more generalized, such that if a token is not actually in the original vocabulary, it breaks it down further. So it breaks it down into characters and then pairs of characters. And then it looks at which pairs of characters have the higher chance of being together. And if it finds that these combination of characters are more are found more in the original, in their vocabulary, then it is then assigned to that token ID. So for example, unfamiliar word here is then tokenized as unfam, ilia, and also word, because it breaks down and then kind of combines it. Sometimes if it's it can also tokenize just single letters, depending on the likelihood of the letters being together in a word or in a token. So they didn't build this tokenizer, the byte pair encoding, from scratch, like what they did previously with the simple tokenizer version 1, version 2. Here, because it's a more advanced tokenizer, they use the tick token library, which is from OpenAI. So after installing tick token, and then you can import it. And here they instantiate the tokenizer by calling get encoding method and passing in GPT-2. And then similar to the previous example, the text example here is, hello, do you like tea? End of text, in the sunlit terraces of some unknown place. And they call the encode method, pass in the text, and there's another parameter in the method called allowed special. And they pass in this end of text here. And this is what the ID token IDs that are generated by this BPE tokenizer. And testing it in reverse, so taking the integers here and passing it into the decode method of the tokenizer and printing it, it was able to actually return the original string. So unlike the simple tokenizer version 2 above, where hello was replaced by the unknown special context token, here the tokenizer was able to return the original text. So here's another example, passing in this word AKWIRW space IER. How does the BPE work? It breaks it down into the tokens AK, because the likelihood of AK is higher than the KW, for example. So AK is a token by itself, and it has its own ID. W seems to have the higher likelihood of being a single letter, then that's tokenized by itself, and then IR here is tokenized, and then W similar to this one. Space, so as I mentioned previously, some tokenizers actually encode, space. So yeah, encode the space character. So for example, this tokenizer does, and IER is then tokenized also, because there are many words that have this combination of letters, tier, peer, and so on. Okay.
Question.
Yes.
What is the size of this vocabulary? I mean, it has to mostly consist of the parts of the words, because if we want to include all the possible variations of parts of those words, so the biggest part has to be from these parts of words, not the words. I mean the words about 20%. The other part is from the parts of words. No, it just question, because if we want to include all the possible variations.
I'm not sure I quite understand your question.
Yeah, I also didn't understand your question, Hugo.
For example, if we will split all the words into the parts, yes, like in this tokenizer, so the amount of the parts will be larger than amount of words. No?
So for example, do you mean this word AKWIRW is then split into 1, 2, 3, 4, 5
Yes,
tokens
yes.
instead of just one
Yeah,
token?
and if
Yes.
and if we split each word into the these tokens, so the biggest part of this vocabulary will consist of these small tokens, parts of the words. No?
Yes.
I'm not.
Yes.
Okay.
Yes. So the vocabulary can be very large.
So is it a problem or not?
I think the constraint is the memory. I guess.
Compute, right? Yeah.
Yeah, the compute.
Yeah.
Yeah,
If you have, yeah.
Mhm. I
because
think,
it's the most
mhm.
straightforward way is to tokenize every character.
Yes.
But it's like taking a lot of resource, so we combine them together.
Yeah. Because as what Frank mentioned, if you have if the vocabulary consists of each letter, just like A, K, W, this can be then tokenized into 1, 2, 3, 4, 5, 6 tokens, right? But by having combinations of the of letters as individual tokens, that actually decreases the amount of tokens that can be generated. Yeah. So
Okay.
for example, here some unknown place is a long word consisting of let's say 4, 8, 9, 10, 11, 12, 13, 14, 15, 16 letters. So the maximum tokens that you can generate if you were to tokenize each letter would be 16. But if your vocabulary had the word some, unknown, and place, then you can split this into just 3 tokens, right? Instead of 16. Yeah.
And
I think Ramon has some comments too.
Oh yeah.
Yes. Ramon, do you want to say what you said?
Yeah, so in terms of the tokenization part, I think in the past, what people would do is that you would do this thing called stemming, where for certain tokens, so like let's say the word running versus jumping, it would just be modified so that it would just be run and jump. And that would simplify the terms a little bit more. And so that would make, let's say, getting like the word frequencies a lot more easy and or efficient. But to my understanding, the benefit of also doing the the binary pairs is that, let's say you have the word, you never saw the word jumping, but you saw the word jump, and you also seen like, oh, if you have ing, that's like changing like the action. So the model can kind of understand that by combining these two together, I can like do more operations on like just the words itself. So there is a benefit on having these separate, smaller building blocks in a way.
Yeah.
So,
Thank you. Thank you. Okay. Are there any other questions before we continue? Yeah.
So like if you're confused, like so you can use it to like you can type in the words, and because I tried the same examples and it's pretty similar like the way to tokenize.
Yeah.
So it'll have
This is
UX.
from OpenAI.
Okay.
Yeah.
Yeah. So like tokenize it.
I think ours is too far off. There's a link there. We can click on it at the end and just try, or we could even just copy the text and see what we find. But the platform OpenAI.tokenizer is a good place to try and just see what we find. But yeah.
Okay, so the next section is regarding how we would like to train the LLM, because the LLM, the aim of the LLM is to predict the next word. So what we want to do is how do we sample the text so that we can have a training training set where we have the input and also the target. So for example, if the input is LLMs, we want it to predict learn. So this is a pair of input and target text that we can use to train the LLM, which we'll be learning in further chapters. So what this section is explaining is using sliding windows to generate this pair, so the input and target. So it goes through word by word, and then the target is actually the list here, and the list of the word and a list of words +1. So +1 is then the target. And by shifting this across, then we can have we can generate different training data points consisting of the input and also the target. So this is where they explain how to do it. They encode the raw text, and so this is the raw text is actually the whole, all of the whole short story of the verdict that is downloaded, and then encoding it using the tokenizer. This is the BPE tokenizer, and the length of the encoded text is 5,145. And then here they take a sample of it. So what they did was they throw out the first 50 tokens, so from 50 to the end, and they set the context size to 4. So what this means is that if we look at the example above, the context size refers to the size of this input here. So they take 4 tokens. So this is the size of the context. So if it was 1, then it would just be 1 word, 1 token. So as we can see, they take the context size as 4. So it's and then the target, which is usually assigned as variable y, is 1 token after the context, the target, the input, sorry. So here in this example, the input is token 290, 4920, 2020, 2241, and 287. So if this was passed into an LLM, for example, we want it to predict the next token, which is 257. So this is the training pair of the input and also the output. So
Why do they skip the first token?
why does this keep the first token?
Why do they skip the first token 219?
Because of the context size.
Okay.
You only want to include the size is maintained as 4.
Mhm. So after the prediction, they have to add the predicted word to the X and drop the first token to compare with the ground truth label. Yes.
No, I thought, and I think this is you know, so I think I didn't understand why the encoded text is 50. Like, why do 50? But the context size, I think, is random, right? It does. It's just that you're keeping like a window of 4 things and moving down to predict your next word, right? So if you go, if you scroll up to that part, right? So I don't know what would be the context size for this, you know, right, as you predict, but I think that's why they try to just move on to the next one. That was my understanding, but I could be wrong.
Okay.
So why did they do 50? So they threw away the first 50 tokens.
They say it's more interesting.
It's more interesting.
Yeah.
That's why in the book they just say it's more interesting to remove the first 50 tokens. So, and they sample that. I think regarding the context size, is this like a hyperparameter that you can, like, because it depends on your batch size, and then it comes down to the context size, how big you want it to be, and then and we want to try and keep a consistent size for all, so that it fits nicely into the LLM.
Yeah, so I quickly searched, right? So the context sizes can also be thought about the context window, right? And right, so this is the maximum number of words that you usually can put in, right, in your review text. So like GPT 3.5 as Turbo has a context window of 16,000 tokens. And context windows are important for AI models because they help them recall information and understand the nuances of language. So I think it's just sort of like, how much is it going to keep it in memory, you know, is what you decide in your context window. And I now that I think about it, you know, it's probably like, I think it would be the past messages included, you know, like when you have your chat playground and you set, if you're using the API side and you set, I think this is really how much should you remember.
Yeah. And adding on to that, if we have a small context window, there's going to be a lot of noise because the probability of predicting the next word will be harder. Instead, like if you have a more bigger context window, your noise would be less because the probability of predicting the correct word is higher. Yeah. So in this example, they set the context size to 4.
You know, I don't want to break your thing. Oh, okay. I even see it below there, right? So, you know, down there, I was gonna say we should just run the decoder for the digits and see, because I think if you look at it from a visual point, it kind of helps you, right? So you can see the first one is like 290 is and, right? And then, but the next one is established, and then now you have and established, then himself, and then and establish himself in, and then and establishes in you know, right? So that's super interesting. And I think as you go through the notebook, you could go back and change the token size and see what the response would be. That would be like a good experiment. Irene asked, is it because Y will be the next X? So they want to keep, yeah, probably.
Yeah. So in the next stage, so I think this is the second name or the third. It's mainly discussing how we can the strategy for more efficient data loader. Here's they basically use the PyTorch data loader, and they create this dataset class called GPT dataset v1, and they basically encode the text using the tokenizer, the BP tokenizer as previously, and then create this using the sliding window that was just shown, and add that into the input and target attributes. And they convert it into a torch tensor. So then they create this function that we can use to easily create the data loader and just modify the input text, the batch size, the maximum length. So the maximum length here, I think is they use max length here, but I think it's the context. And then the stride. So the stride refers to how far the sliding window will slide to the next set of tokens, or how far it will skip tokens, and then shuffle and drop last. So they create a function which generalizes the dataset building. Again, they load the verdict text. They create the data loader using the function. They input the raw text. They set the batch size here as 1. The max length, so the context window is 4, and stride equals to 1. So that means the sliding window moves 1 by 1. So for example here, if we look at the first batch, the X, the input is 40, 30, these sets of tokens, and the Y is 3, 16, 7, and all the way to the next token, which is 1807. And if we look at the second batch, so it calls the next function. And because the sliding window is 1, so the X goes from 40 to 367. And that's what the X is right now. So for example, if the sliding window was 4, that means it would move all the way to 18. Sorry, what did I say?
Is the sliding window stride?
Oh, sorry, stride. Of 4, it's 1807. Okay. And now, okay, so this is a visual representation of the stride. So if the stride is 1, then it moves 1 token down, and there's overlap between the previous set of input target and the next one. Whereas if you have the stride as 4, it moves down to here. Okay.
So
and then
one thing people can do, I think just as a learning exercise, I mean the presentation of this is pretty good, right? So it starts from very, very simple to showing you how do you even end up with such a big loader. I think just looking at being the best way to learn this is to read the sentence and then just estimate, like say stride 5, and think what the right word is, and then change the code and see where it goes, right? Because then that really emphasizes on understanding.
Yes. Okay. So that was with batch of 1. Now the batch size increased to 8, and the stride is changed to 4. So when we increase the batch size, you can see the number of rows increased to 8. So 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 pairs of inputs and targets here, and each row, the position corresponds to the pair of inputs and targets. And because of the stride of 4, as you can see, it starts from 40, and then the next X is 1807, which is this, which is the predicted next, which is the next token after this, and so on. Okay, yep. And okay, so this is the second section. So that the first section was converting text to the IDs, and then they also had this efficient way of loading it, creating the data loader. And the second section is taking the token IDs and then turning them into the embeddings. So turning these discrete numbers into the continuous, in the continuous vector space. So the example here, the simple example, is taking a token with a size 4, so 4 dimensions here. So 2, 3, 5, 1 as an input. And let's say they had a vocab size of 6, and the input dimension is 3. So the output dimension is 3, which means the output token size here is in 3 dimensions. So 1, 2, 3. We have like X, Y, and Z coordinate. And then the PyTorch has this embedding class that can be created, which just takes in the vocabulary size and also the output dimensions, and we get this layer, which is the embedding layer. This layer has weights, and these are the weights if you print it out, and these weights are first initialized by using it can be randomly initialized. There's like algorithms to initialize them so that the training can be much better or quicker. These weights are then updated throughout the training cycles, training iterations. They are updated using the backpropagation and so on. So this will change in the training. So when the torch tensor is passed in here, for example, into the embedding layer, it outputs this this vector of size 3 here, because the output of the vector is 3. It is basically taking the third row, like 0, 1, 2, 3, the fourth row, sorry, because Python starts at 0, the counting. So you count 0, 1, 2, 3, and it outputs this row here as the output. So that is the embedding for a tensor, for an ID token of 3. That is an example. So if we remember input IDs, it's 2, 2, 3, 4, 5, 1. That means it will then output the embeddings based on the weights here. So 2 would be 0, 1, 2. It's this line here is being output. And then 3 is this one. 5 is the last one. And 1 is the second one, which is up here. And so this is the embedding. So this is showing conversion from the token IDs to the continuous vector space, which is the embeddings here. This is the graphical representation showing the input. So fox jumps over dog. We have 2, 3, 5, 1 as the token IDs. We have the embedding space here. And then we call like 2 here. It basically pulls the third row, which is 0, 1, 2 here, and outputs and converts number 2 here as this embedding token, and so on. So number 5 will take the last one and then output it here. So converting 2, 3, 5, 1 into embedding space is actually, it will give us this array. Okay, any questions? Okay. Last section is encoding the word positions. So how do we, because in this section here, it doesn't tell us where the position is. It just tells us the embedding for each token. So how they do it is actually using adding what is called positional embeddings. So in this example, for simplicity, they make the embedding token is 111. So the first word is assigned 1 point something, 1.1, 1.2, 1.3. So the first dimension in the first token is assigned 1.1. The second dimension in the first token is assigned 1.2, and so on. And they just add the positional embeddings. So 1.1 plus 1 equals 2.1, and so on. So 2.1, 2.2, 2.3. And that goes on for all the tokens at each position. So the larger the position, then the higher the number would be. And this modifies the embedding, which is the original embedding, by the corresponding position. And finally, they give an example of this. So they show the total vocabulary size, and here they increase the output dimension. So previously it was just 3, now it's 256. Now they create a batch size of 8 with 4 tokens each, and the size of the tensor is 8 by 4 by 256. So this is a large dimensional vector. And here we can see the token IDs for the first 8 batch. For the first batch of 8 data points. And then it is passed in to the embedding layer. And here it's still showing that the size corresponds to 8 by 4, but the output embedding dimension is 256. So for each token, the output embedding dimension is 256. Yeah. And here it's showing the context length equals to the max length, and adding the position embeddings. So what torch arrange does is that it creates a torch tensor starting from 0 all the way to the maximum length of whatever is input here. And then that is the positional embeddings. And here's the shape, so 4 times 256. And as previously shown, it's basically just adding this to the original token embeddings, and it changes the input embeddings. It does not change the shape because the shape remains the same, but the values change corresponding to the position of the embeddings. And this is the overall final schema that we've gone through from this chapter. So from the input text, we learn how to tokenize the text. We learn how to transform the text into numbers here by using unique token IDs. And then for each token ID, we learn how to do the embeddings, transform it into the continuous vector space. And by adding positional embeddings, we can know which token goes first, last, or the position of the token. And that is then the final embedding that will be used in the next steps. I think that's it. Yep. Okay.
All right, go ahead.
Oh, awesome.
Here, please.
Yeah. So great job with this. Questions, feedback?
Thank you.
Hello, everyone. Thank you, Theo, for your presentation. That was awesome. I just had a question, not about I was wondering, when does this tokenization take the meaning of the words? I mean, when does the machine learns the meaning of the words? For example, if you if you convert, for example, the word hello to a token that is hello, not separated by, not converted to HELLO, maybe it will have some meaning. It will learn the meaning of the word through training, while embedding them to these vectorized matrices. I was wondering if we can change this tokenization, this embedding system for our medical, for specific medical terms we use in, for example, reporting radiology, or different terms for different diseases in the medicine. I don't know if I was clear.
Do you mean that we specifically create the vocabulary for like a specific task, like for example in medicine, like a specific domain?
Yeah.
So yes, so if you, it's basically modifying the vocabulary in the tokenizer, I guess, if you're referring to the simple tokenizer, this vocabulary, what it's being trained on in the beginning. So for example, this simple tokenizer, which is instantiated here as a tokenizer here. So this tokenizer is specific for the verdict short story, because it was trained on that. So, but if we were to I think generate the vocabulary specific to the medical domain, then the tokenizer would be, I think, specific for that, for medicine, for example. Regarding your first question, where does the algorithm understand the meaning? I don't see where it does. It's the next chapter, because there's no operations that look at the distance. So as what is shown in the word to vec here, I think. In this case, you can see that there's like, you can actually see the distance between these data points here, these words are closer, are shorter, are smaller than the distance from this cluster to this cluster. So when there's like operations that look at the similarities, like cosine similarity score or any kind of metric for measuring the distance, then there is kind of like a learning or I think that's where the model learns that words that have similar meaning should be closer to each other. So I think this chapter is mainly like creating, transforming the words and giving that a coordinate system, like where is it on the coordinate system at the time, like the number, like transforming it into the continuous space.
Thank you.
Any other questions or comments? So I was playing around the link that was shared by Awares, which is the let me think about this platform.openai tokenizer, and I think it's interesting. So I said Judy Ricks, and it turns out that there's no Ricks, you know, in the tokenizer here. And I think to me, when you see 4 tokens, it's probably doing that split that Theo you are identifying, and this is what would end up being the numbers, right? And so if I maybe change this to you know, so it's still I don't know why it's still doing that, but I was to speak in Swahili. You can see, you know, so now it starts to really go up as it tries to come up with new words. I think one thing to remember here is the fact that this concept of self-supervised learning for the large language models, where you can make up new words, right? Because you know how it keeps going and processing and saying, okay, I don't know this, but I know this portion of the word. I think you showed us that, and I think that's important, because you never really, you know, it sees a lot of text, and then it may see some text that is related, but that is not like a known word, and then it comes together and tries to make up that word and then indexes it. I think it's something good to remember in terms of text processing, especially now as we see the problem where I think when they tried to encode some Chinese words, they got a lot of pornography, and just so people are starting to feel like probably the data quality of your original text and where you get the data from is more important than just showing the models more data, right? And so that's one. And I think the concept of embeddings, when we see like the n-dimensional space, is it's not really what Amiral is asking about, the understanding, but I think it gives you a better sense of like the positions, the semantic meaning of what the word could mean. And that's, I think, to me today was really understanding what a token ID is and then what the embedding is. And it's really trying to make this in a more understandable form within the large language model, whether it's that continuous space. And that's why, you know, it's so hard for me to like make the jump from, okay, here's just a simple word, but you're saying, look, they are like 700 dimensions that this word can be represented, right? So that's another point. Okay, so what was some lessons from you, Theo, going through this chapter?
For me, I learned how to actually, I actually learned how to transform the words into embeddings. Previously, didn't understand that. The tools that they used, and now that it looks very simple to actually implement this. Yes.
You're doing quite a lot of this. I think it's going to be interesting for you.
Yes.
Frank?
So yeah, so my comment is that the tokenization technique, the subtoken, the BPE, won't work for Chinese, because in Chinese each character has its own meaning, so we cannot separate the characters. So yeah, I don't know how if we want to train a large language model in Chinese.
Yeah, that's interesting. Okay. Amirali, did this, given that you talked about this chapter last time, and then now seeing this, is it more confusing, or what are some of your lessons from this?
No, it was so interesting. First, I thought that the model in general is trying to predict only the next word, and now I realize that it's going to predict a phrase with the addition of the next word. It's not just the next word. For example, LLM is stands for large language models. It's going to predict all the words in the sentence plus the word in the end. I thought it was just predicting just one word at a time and not looking at the text behind. And another thing is that now we know when we are using LLMs and we set the token limit for example, 3,000 or 2,000. Now I know what that means and how to manage to use that properly.
Awais?
So I previously used Tokenizer, the one OpenAI, and so when you put certain words, it would break it down into like multiple tokens, like rather than having single word for like single token. So now, like, thanks for the presentation, and like I was able to understand now, like why certain words have multiple tokens.
Yeah, I mean that the link that you shared is actually really nice to just understand. If you just you know, for people who don't want to program or do anything, but you're like, what, like, just get a better understanding. Then even like for myself, like I couldn't be like, should I really move the window? Like, how much context is important? How many words should it, you know? I think that's super important to even as we move down to really using this to optimize the function of your prediction. Okay, Irene, if you're able to.
Sorry, hi. I do have a question about the positional embedding. So it seems like it just adds a positional embedding to a text embedding. Does it just like because they in the text field they also said the text embedding is like a weight. And adding it, I don't know how adding the positional embedding would like give the information of its position. Sorry, it may be a weird question if I am not clear. I'm just thinking that it changes the way, so the same word, they depending on different position, they have different weight.
Yes.
Okay. So the vocabulary size is just getting bigger and bigger because each word have different versions of embedding based on the position.
The vocabulary size is maintained. It's constant, unless you add or extend it. It's the value of the embedding changes based on the position. So it changes, like as you said, the weight. If it is at the beginning of a sentence, so the weight is smaller because the position is either 0 or 1. If you go on to like the position is 100, then the embedding will be then added with 100. So it will be a big number, the embedding.
Yeah, but also the weight, I think they use a random number. Would that cause like after adding a positional embedding that two words have the same weight? Would be the case? No. Okay.
So I think the way to do it is to normalize the weight first. So it's between 0, -1 to 1, something like that. So when we add 1, 2, 3, so they won't overlap. I think that's the. I'm just guessing. Yeah.
Okay.
So there's different, like you mentioned, weights. There's weights in the layers of the model, like the embedding layer that has weights, and that's a trainable parameter, like trainable. The values will change based on the iterations of the training, it will try to optimize the weights so that a particular token matches the correct like position, and it predicts the correct token actually, yeah, also. But and then in terms of, you mentioned one word can have different weights based on the position, is also something different, where the word that comes earlier has a lower weight than a word that comes after. Like, even though it's the same word, they have the same embedding token, but if they are positioned further down the sentence, their values would change by the position of that word in the sentence.
So they
So
how
that's-
to like, yeah, so how to like converge to one weight for one word, or they never like,
So it's one weight for one token.
Yeah.
Yeah. So
You mean
the weight won't
the
change,
weight?
but the position of the weight will change. Like
for
you can
for
think of that as shifting in the space.
Yes.
yeah, like for
When you
the
mention weight, it's the embedding token.
Yeah, it's the
Yeah.
embedding token.
So the embedding token remains the same for that word,
Uh-huh.
but it will change based on the position.
yes.
Yeah.
Okay. Okay.
Okay, Diego? Anything new, Lance?
Yeah, I would like to say thank you for the presentation, especially for the coding part. It was useful, and I learned how to deal with words like splitting apart and adding to the vocabulary and so on and so on.
Okay, great. I think we'll meet again in 2 weeks for chapter 3. I encourage people to just go back and reread chapter 1 and 2, right? And then try the notebook, try to play around. Personally, I'm a visual learner. I need to pick a sentence and then try it, and then, finally understand it. Highlight some of the big components and then correlate them, because this is such a foundational block about what to do next, Okay. Great. So thank you so much, Theo, and see you